Good morning, Mr. Chairman, ladies and gentlemen. My name is Coulibaly Mohamed, and I am a mathematics research at Institute for Mathematical Research in Coulibaly. As part of our work to fight against dengue fever in Coulibaly, we have been working with Dr. Mian from our country's National Institute of Egypt to develop a model of a dynamic of vector-borne disease that takes into account all types of transmission, both vertical and horizontal. The organization of our presentation is the following. At first, we'll tell us our motivation. After, we present our model of vector-borne disease, and we continue with some characteristics of this model, and we will achieve our presentation with conclusions. We were motivated by the desire to help stem outbreaks, study more the interaction between host, vectors, and pathogens, assist in decision making. And for that, we have developed the following model, which the graph is this one. Our model has 7 compartments. SH is the compartment of susceptible humans. EH, the compartment of exposed human. IH, the compartment of infected human. RH, the compartment of recovered humans. In vectors, we have SV, the compartment of susceptible vector. EV, the compartment of exposed vector, and IV, the compartment of infected vector. Mu, this constant represents the new number of susceptible humans by unity of time. And this one, the number of susceptible vectors by new susceptible vectors by unity of time. Delta is the natural death rate in humans. P is the natural death rate in vectors. And this constant nu represents the death rate from the disease in humans. And this new constant, eta 1, represents the proportions of newborns who are infected in the populations of humans. And this newborn is infected by a new transmission, which is a maternal transmission. We have the same figure in the populations of vector, where eta 2 represents the proportions of newly born infected in the populations of vectors, and this infection is due by maternal transmissions. And we have in our model, we have 2 types of transmission. Beta 1 is the transmission between infected, the rate of transmission between infected vector and susceptible human. And beta 2 represents the rate of transmission between susceptible human and infected human, because we consider that with some vector diseases, the blood, for example, can permit to transmit the pathogen. Okay, we have also some constant. This constant represents the rate at which an exposed human becomes an infected human, and alpha is the rate at which an infected human becomes a recurrent human. We get the same thing in the populations of vectors. A mathematical translation of our model is the following. We get 7 differential equations which permit us to get a mathematical study. So we prove that our model is a biologically significant model because it lives in a positive set and it has a positive solutions. And with some conditions which depend on some constraints of the model, we prove that the reproduction rate R0 exists. And we also prove that the disease-free equilibrium is locally asymptotically stable. This is an important condition which permits us to show that it's possible to eradicate the disease, because we can tend towards this state, which is a disease-free equilibrium. And after this study, pursue with another study, which is the sensitivity analysis. We prove that the reproduction rate depends strongly to beta 1. If you reduce beta 1, a small reduction in beta 1 gives a very great reduction in the reproduction rate. But we have not shown the same thing with beta 1s, the second transmission rate, because it's costly. It's very costly when we make our computations. It's very costly to reduce beta 2. So the control of the disease is possible with the control of these parameters beta 1. We show a visualizations of R0 as a functions of beta 1 and beta 2. This visualization corroborates our conclusions. We get also some numerical simulations. The first simulation, we make the first simulation with the data of our country. When we reduce very strongly beta 1, we get these curves. The blue is the trajectory of exposed human, and the red, the trajectory of infected human. So we can see that with a certain reduction of beta 1 is possible. It's very possible to slow the disease. In conclusions, can say that it's very important to consider most transmissions in the dynamics of a Vector-Borne. And our mathematical studies prove that it's possible to eradicate the disease with the control of a rate, which is the rate at which an infected vector transmits the pathogen to a susceptible human. So we find that it's very important to continue this study with an integrated time with mathematicians, epidemiologists, climatologists, entomologists, and decision makers. And that will permit us to have more control on some vector diseases. Thank you very much for your invitation, and see you next time.